halogenation that should be classified as radical alkene halogenation. So that is, these are the radical reactions here. So there's two big term things that work here. We are adding chlorine in light, and then the other one that we have is using bromine in light. So with the chlorine reactions here, some notes that we need to make about it. Mechanistically, it is fast. It is a fast reaction. It is unselective, so that's the first note there. It's fast. It is unselective. And what I mean whenever I'm saying that is that it goes all over the place. It doesn't have any particular carbon that it pretends to attach to. And the thing that we are also going to have, we're going to have, because it's unselective, we're going to have many products. Okay, so in this reaction, the rate limiting step will be exothermic, and I'll switch colors to indicate that. It is exothermic. So moving on down there, you're going to get a mixture of products. And the transition state resembles the starting material. So whenever I use the words exothermic, just to remind us, that means that we have a delta H. Value for exothermic is negative, and I'll just go ahead and draw ourselves a little reaction there. So that means that the reactants were actually in a higher energy state than the products. So that's what that means. Moving on to Br2, radical reactions of an alkene with Br2. So just how that was fast and selective, these are very slow, but they are stereoselective. Or just more or less just selective. That's the thing though. It's always going to break the weakest bond. So it's always going to break the weakest. Weak carbon-hydrogen bonds will be broken. You already know, well, I'm assuming that if you've gotten this far, you understand that allylic are the weaker, and then secondary to that is tertiary, and then secondary, and then primary carbon-hydrogen bonds are really, really strong. So the advantage of using this, unlike this, I can't think of any reasons to actually use chlorine for producing things because it's going to get products all over the place. But this, I can very easily predict what the major products formed are going to be because it only is going to have one product formed. Only one product, which is nice because that's useful for doing things. And then the more faster, so that is the more stable radical is formed faster. Okay, so just how this was exothermic, this reaction here has a endothermic rate limiting step. And so what does that mean? Well, that means that delta H is positive delta H. And as I draw out my little reaction coordination here, this means that the reactants were in a lower energy state than products were. Okay. Stereochemistry, let's talk about the stereochemical effects of this. So obviously if you have an achiral reactant, you're going to either, well, okay, I'll just branch up here. So if we have an achiral reagent, I'm just going to say R, this is going to give us two things that can happen. We can have an achiral product, which makes sense, or we can have a racemic mixture. However, that's not really what's important. Knowing is that if we have a chiral reactant, this is going to yield to give us, if reaction occurs at stereocenter, consider the mechanisms. What do I mean by saying that? Well, remember that radicals are trigonal planar. And so if you could kind of imagine this, looking at an sp2 hybridized carbon, kind of head on or angle on, it's not too bad, I suppose. So that at any given point, that could be, that radical could be in the top, or it could be in the, do it in blue, in the bottom. So these radical reactions can happen from, so say you have, you know, I don't know, bromine there. I'm just going to draw it like this. You can have radical reactions happening at the top, or you can have radical reactions happening at the bottom. Either one. So it's something you want to keep in mind. Cool. Moving on. So let's talk about NBS and allylic radicals. So remember, allylic radicals are anything with, or allylic carbons are anything that have this generic structure. Allylic radicals are the most stable radicals, and therefore they contain the weakest carbon-hydrogen bonds. And I want to make a note that regardless of what other stuff you have around here, so this could be anything else, you could be attached to anything else, if you see this, you know you're working with something that is an allylic radical. So one of the reactants that we can use is known as N-bromosuccinimide, and that's not so important so much as that this is the only way to brominate allylic carbons. I'm just going to say allylic carbon radicals. So, unfortunately, this is a very slow reaction because obviously if you take an alkene and you expose it to just Br2, you're going to get vicinal dihalide. But N-bromosuccinimide is going to slowly but surely decompose. So let's just draw out the overall reaction. The overall reaction is that you have an alkene that contains an allylic carbon. We go ahead and react that with NBS. And I believe you can only use peroxide, but I think you could also theoretically use other compounds that could generate radicals, light. Not a big fan of heat. And we have added to that is a bromine to that. Okay, so let's kind of talk about this. This reaction here is going to give us a product mixture. So we're going to use a little rule to let us know that. So if we have for an asymmetric compound. So this is a symmetric compound. This is the only product that we get. But if this was asymmetric compound, you take the number of allylic carbons, so I'm just going to say Ca, whatever number, how many of every one of those you count, you multiply that by 2, and that's going to give you the number of isomers that you're going to get from that reaction. And the reason why we use this is because allylic carbons, and the reason why allylic carbons are the most stable radicals is because they can do, so they are resonance, stabilized radicals. So I'm trying to see if there's anything else that I mentioned. So obviously this is the only way that we can do this is with these structures here. So just keep in mind that you have to deal with that for asymmetric compounds. But other than that, it's a pretty straightforward reaction. And I'll talk about the mechanism later. Yes. Okay. So we have, after that, should be, I should have made this only works well with symmetric compounds, and it will react with all, excluding the resonance hybrid. It's obviously very productive. You know what you're going to get. You're only going to get one product if it's a symmetric compound. But let's talk about anti-Markovinkov addition. And what I mean by that is where we have, say, an alkene here. The rest of this is all hydrogens. It's allylic. You could think of it, kind of. The rest of those are hydrogens. So I go ahead and treat this in a reaction with hydrobromic acid and some type of a radical form. I'll just say peroxide or light HB, one of those. And whereas with this, if it was normal Markovinkov addition, we would remember we'd have the bromine would be on the most substituted carbon. Well, now because of this, because of radical formation, because radicals don't shift. Keep that in mind. I don't think I mentioned that actually last time. But radicals don't shift. Sorry, that's a single bond there. Single bond. There's a hydrogen there. Hydrogen there. What have we added? Well, we've added a bromine and a hydrogen, but the bromine is now on the, so I'm going to make a note that this is on the least substituted carbon. That's insane. That's really helpful. So think of all the types of SN2 reactions that we can do now that we have a primary alkyl halide. So that's pretty helpful. All right, so now I'm going to talk about the mechanism behind radical HBr addition. So kind of, I guess, going through here. And the book and Dr. I can't say his name, stress the radical HBr addition of not only the two ways of happening. So I'm not going to talk about termination reactions just because that's pretty self-explanatory, or maybe I'll just write it down here that termination is where you have one of your radicals that you formed in your chain reacting with something else that is a radical, and they come together and they form a stable initial product. And that can be anything. They don't really care. But so I'm going to branch this off into the three sections. There's initiation. That step's important, and then there is propagation. Propagation. So the thing with initiation, the only thing that I've seen that was made sense is I've heard that you can use light, but for the purposes of this, I think they want you to specifically use peroxide because my book gives me a mechanism behind peroxide initiation of radicals. So we obviously have ourselves a little peroxide here, and peroxide, those single oxygen bonds are really unstable, and so it's going to undergo homolysis, and what that gets us is RO and then a radical on oxygen. So HBr comes along, blue, HBr comes along, and being a good radical, seeing a hydrogen bond there, we go ahead and do a little half reaction, well, not a half reaction, but a radical reaction that takes that away and results in a alcohol. But that's not really superbly important so much as the fact that what we've gotten out of this is, and I'll switch it to green, what we've gotten out of this is a bromine that is now a radical. And this bromine is going to run into Well, I'll also use that's the same, I think, example that I started off with, but it runs into an alkene. So what does that alkene do? Well, it's electron dense. It's going to be attracted to that. So that's our first reaction there. That is our second reaction there, and then it's going to go there. So remember the advantages of having that allylic radical. See, we now have that's the most stable radical, and because that is the most stable radical, sorry, I don't know why I keep drawing those. That's a single bond, but it's a secondary radical, and because it's a secondary radical, unlike when we were talking about carbocations, secondary radicals do not shift. You can't do a hydride shift to change that. I'm going to go ahead and make sure that I clarify that that is a BR that is attached to that carbon. And so, going to draw another hydrogen in there in place, but that's not so important there. So much as the fact that we just added a bromine to the least substituted side. I guess that's the most important thing. But one of the other things that happens is there is another HBr molecule here that is going to do essentially what happened over here. Goes there, that goes there, that goes there, and so what we end up with as our final product is carbon, 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 hydrogen, 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 a bromine there, and a hydrogen there. And that is really, really helpful. So this first step here that I drew in green, where's green? This is the initiation step up here, and then the propagation step is the one that I've drawn in white and blue. Now I need to also clarify that this only happens with HBr. HCl gives us no reaction. I don't know why exactly. I think it has to do with the bond dissociation energies. This step is kind of taxing. Remember, this whole reaction is pretty slow, but that's just not something that happens. So moving on to the actual mechanism behind N-bromo-succinimide, and I probably should have rearranged these differently, but who gives a shit. So N-bromo-succinimide, like any other, there's two parts of it. There's initiation, I'm just going to say I, and then there's the propagation step. So the initiation of N-bromo-succinimide is, and I'll try to see if I can draw it here, there's two carbonyls, there, and that nitrogen is bound to a bromine. So presumably we're in light or peroxide, something that's going to cause these things to happen. We have a homolysis occurring to give us Br radical and a I don't even know what the name is for that compound, a radical on a nitrogen, but that's not what's so important. Well, so the next thing that's going to happen is the propagation phase. This bromine, this radical bromine, is going to react with an allylic substance. There's a hydrogen bond attached to that, or hydrogen bound to that, so hydrogen bond. And being a good little bromine that it is, that goes there, and that goes there. Kind of getting messy, but blue. Come on, Danny. It's really hard to draw cyclohexyl or cyclic molecules on this thing. So we get not BRH. Oh, I'm tired. We get HBr as one of the products of this reaction. That's not so important. I'd like to know why it doesn't just react back with I mean, I guess it does react back with it. It just wouldn't be much importance. So doing what it does also in bromo-6-cinnamide, because you have bromine radicals forming. Those bromine radicals can react with each other to form Br2, and that's one of the other things that we get from that. So Br. This is a radical. It does what most radicals do. It causes radical reactions to occur. And what we get is our next step. An allylic bromide. So, that's all I have to say about that. Next mechanism is radical halogenation mechanisms. This is how most halogenation tends to work, but I'm just going to go ahead and classify. There's an initiation, propagation, and then termination. Whoop-de-doo. I probably should have put this at the front, is that we have homolysis of a compound. So we have a chlorine attached to a chlorine. This is the only time that homolysis happens, at least in a generic radical propagation. I'm going to do electron pushing arrows, or half Kushuk arrows in that. And then that reacts to give us two radicals, but they're reacting with each other, and I'm not going to really stress that. Obviously, they're reacting back and forth. So I'd like to know a little bit more of what makes radical reactions chain reactions, and why they don't just automatically come back together. But anyways, next is propagation, which is where I'll do that in blue. I meant to do that in blue actually. Propagation, and so what is going to happen is say that there's a hydrogen there, carbon, carbon. Nobody really cares about that. I'll just make that a hydrogen there and a carbon there. So it's going to do green. It's going to do what I've been drawing happening over and over and over again. It's going to react here, move forward, giving me a radical substance there. So in this context, I have a secondary radical. What else have I formed? Well, not really important, but I got HCl out of this. That's not going to really do much more. But what happens is another homolysis reaction occurs because radicals are unstable like that. So here's this electron here, and then there's another dichlorine or a diatomic compound. And in theory, yeah, of course, it could react with another one of these, but that's not going to give us anything that's superbly new. So it's going to do, again, what radicals do, reacting there, and what we get is blue next there, C, C, H, C, sorry, and a chlorine attached to it. Now, chlorine is obviously going to go do other things, and it's a chain reactions because you also get another one of these, and then it'll probably bump into another. That's the termination behind the two.